really sure at the moment. Oh, sorry. Sorry, here was a mistake. Can you see my slides now?
Yes.
Yes, that's great. Then has it worked? Yes, that was the last slide from the last lecture, I think. You have seen that we have different definitions of the areas of measurement and instrumentation in different countries. And that was, let me say, the end of the last lecture. And now we start with the concrete content of measurement and instrumentation. And the next time, what I will tell you is valid for every field of measurement. Everything what you would like to measure, for that is valid. When you measure a temperature or a speed or a voltage or, yeah, let me say strain or what else, that what we speak in the next lectures is valid for everything, and therefore it is very important. That means that I explain you at first the structure of a measurement system, and after this we will speak about the calibration of a measurement system, and we will speak about errors, random errors, systematic errors, two different kind of errors, and all these things are valid for everything what you would like to measure. Let me start with the general information system, and you see here the boxes. The first is the information source. We call it also as a process. A process can be everything. That can be a room. And in this room can be produced an infinite number of informations. For example, the temperature, the humidity, how many people are in this room, and yeah, the pressure, the brightness, everything is possible. And then you have the signal conversion with the sensor. And the task for the sensor is to select one of this information and change this information to the to another layer, for example, an electrical output signal. Important is that the sensor select only one information, and that is in the practice not the case every time. For example, when you measure the brightness with a photo transistor, you have also an influence of the temperature, but that is not that what you want. You would like to measure the brightness and not the temperature, but both informations have an influence. And therefore, the task is to select so best as possible only one information. And then you change it to another signal. We have, let me make this example, you have the brightness here, and now you have a current or a voltage on the output side. Normally, you have then a processing. That means you have an amplifier, you have an analog digital converter, and then a PC connection. That can also be in a different row. For example, if you have an PC card, then you have at first the PC connection, and on the card is the amplifier, the analog digital converter, and so on. But especially for high-end products, you have the amplifier and the analog digital converter outside of the PC. That means that can a little bit change here, but the content is every time the same. And on the PC, you have then to look that you get the right information again back, because you have here, for example, the information on an electrical signal. Then you have an electrical signal, and after the processing transmission, for example, after the analog digital conversion, you have an unified range of numbers. Let me say you have an 12-bit analog digital converter, then you have on this point only numbers from 0 to 4096. That is a range of a 12-bit ADC. And from these numbers, you cannot see what is behind this. Was it in the beginning a voltage or a brightness or a temperature? You have only these values from 0 to 4096. And on the computer, you need now a software where you calculate back the right information. That you calculate back the right information, that the computer get and guidance how to calculate from these numbers the true information. And then you go on a screen, on a printer, that is the output signal of your computer. And from the information technology, we know that where is a source, we have had also a drain, and the drain can be the human, the waste basket, or what else, where the information is going down. What we handle are these 3 blocks in the middle. That is that for what we look in this lecture. You have an input signal, X. X is every time the input signal, and that is the true information. The true information, let me say we would like to measure the brightness, then is this the brightness, the true information. You have the signal conversion to an electrical signal. Today, normally every time to an electrical signal. And on the way, you have influences from outside. You have maybe a noise, you have the temperature, you have disturbances from outside. And you have to avoid these disturbances, of course, but you can not make it to 0. You can reduce it in most cases, but you can make it not to 0. And then you have the signal processing, you have the transmission, you have the analog digital conversion, and then you need the software to get your right signal. And the right signal is the right measurement value is Y, and this Y has to be the same as the X. That means the function of the whole system is every time Y is X. That is every time the aim. Y is X, the aim of every measurement device. When you put 5 kilo on a balance, you expect 5 kilo on the output side. When you put 20 centigrades in the input side, you expect 20 centigrades on the output side. And therefore, this signal reconversion from the ADC number to the right output signal, that is what we where we say that is the calibration or the computer-aided measurement value calculation. There are different expressions for that, but that is one of the most important points, and we will look how it works. Now it is so, yes, I go a moment back. I have told you y is x. It's the only one's right function what we aim over the whole system. But in many cases, it isn't so. It isn't so. It can be linear, but it must not be linear. And here I have now connections between the input and the output side for the static behavior of the system. The static behavior, here is it written, the static behavior describes the dependence of the output value y from the input value x. Normally, it should be y is x, but it must not be so. So, and important is during the static, where is my mouse? Sorry, I must look for my mouse. Now we have it. During the static status of the system, and then is of course the question, what is the static status of the system? The static status is achieved when by no changes on the input side are all dynes on the output side are finished. Both input side as well as output side are in a static status. That means you should have no changes on the input side and you have no changes anymore on the output side. Ideal would be the behavior y is x, but it must not be. It can also be in this form, and you see here you have a linear function with a amplification. The m is the amplification and n is the 0 point. You see the n is not 0 and m is not 1. Normally should be m 1 and n should be 0, that you have y is x. But in this case, it isn't so. And you can also have nonlinear functions. In many cases, you have nonlinear functions, especially from the sensors. And then you can describe the amplification and the 0 point only in a very small point. My point is a little bit big, but it comes from the PDF maker. I don't know why the PDF maker is doing every time such a big point. But theoretically, this point is extremely small. And you have here then the linear function in every point. But we will see later to handle this, to make a linearization, we take a range where we say we approximate this range then with a linear function. That are, by the way, every time very typical nonlinearities. In many cases, you go in a saturation when you increase the input signal more and more. Let me say the brightness of the brightness, of the environment, and the phototransistor or the photodiode is going then anyway in a saturation. That is very typical for many sensors. But let me say, but I go back to this point. We say you have no changes on the input side and no changes on the output side. Then you look for the dependence from the output to the input side. The dynamic behavior is the time, what is doing the device in the time until the static behavior. And now is the question, where is the dynamic behavior finished? And we speak from the static behavior. Here you can say the theoretical definition is when no changes on the input side and no changes on the output side. But when is that theoretically? Theoretically, is that in an infinite time. When you have an, let me say, a thermometer, and you put the thermometer in cold water, and you see how the temperature is going down, or in hot water is going up, but you see it will decrease or increase until a static value. But when you look with a magnifier on this and you make a zoom in this, you will discover that you have every time again a little change. And so the static behavior is achieved in an infinite time. That is its theory. But for practical work, we need a different definition when we declare the behavior, the dynamic behavior as finished. When we declare it is now in the static behavior. And how that works, we will see now. Here we have the definition of the dynamic characteristics and parameters. The dynamic behavior of a measurement system describes the dependence of the output value y from the input value x until the static status of the system. And we have learned already the static status of the system is achieved theoretically in an infinite time. You will normally never get in practice the static behavior. And for clarify that, we look how measure we the dynamic behavior. You have here a function generator, you have the measurement system, and you have a registration equipment. And let me make a very easy example. You have a pot of water, a pot of hot water. That is your function generator. When you measure the temperature, you put a thermometer into this pot of water, and you see how the thermometer is going up with the measured temperature. That means the measurement system is the thermometer, and the function generator is this pot of hot water, and the function is a jump function. You jump with a thermometer from let me say, a room temperature to the hot temperature. It's a jump from one value to another value. And then you see the temperature is going up, what you measure, and the registration equipment that, for example, are your eyes. Your eyes, you look on the thermometer, you see when the thermometer is put into the hot water, you see the jump function, and you see on the other side how the thermometer is going up with the temperature. And theoretically, you get the static status after an infinite time. But that is not useful for the practice. For the practice, you have to say when declare we the dynamic behavior is finished and when is the static behavior achieved. And that I go to this slide, that do we with a range of an rest of error from the dynamic behavior. I have here the rest of error with plus minus 5%, but you can also say plus minus 1%. That is independent. And now you have here the jump at the time 0. In this case, you have also an oscillating device. You see here that can be, for example, a balance. And you see this oscillating will be smaller and smaller. And theoretically, you get the static value in an infinite time. In an infinite time, you will get a static behavior. But because that is not useful for us, we say we have this range, plus minus 5%, static behavior plus minus 5%, and we look for the moment where the output signal is going the last time in this range. The last time, and this is here is this point, and after this time, the static or the dynamic signal is in the range of plus minus 5%. And this time, until this point, we call as the settling time. The settling time, and when we define the settling time with plus minus 5%, we say it's a settling time T95. That means for the practice, when you have in a manual the settling time T95 is 15 minutes, for example, then you know when you read your value after 15 minutes, you are in the static behavior with the rest of error from the dynamic behavior of plus minus 5%. And when in this manual is written the time T99, T99 means this range is plus minus 1%. T99 is longer than T95. And you look where is going the signal the last time in the range of plus minus 1%. And you know the settling time T99, for example, is given with 25 minutes. That means when you read your signal after 25 minutes, your measurement value after 25 minutes, then you are in the static behavior with the rest of error from the dynamic behavior of plus minus 1%. That is the practical definition of the moment where you say, here is the dynamic behavior finished and the static behavior is achieved. And when you have a thermometer makes not an oscillation. A thermometer would start anywhere and would go so and would cross your plus minus 5%, for example, and would go in the infinite time on the static behavior. But also there have you across to this range, and you can say T95 is so and so long, and T99 is so and so long. And for the percent you are free, there are some recommendations. Plus minus 5% is a recommendation, plus minus 1% T99 is also a recommendation, but you can also say when you have a very precise device or a very fast device, you can also say T99.9 or T99.99. That's everything is possible. So that is the most important time. The other times, what I have here, that is not so important. What you should know is the settling time. The settling time and the definition with the rest of error of, for example, plus minus 5 or plus minus 1%. That is very important that you know this, because the settling time is, in many cases, it is given in the manual of devices, especially when you have slow devices. Slow devices, yeah, let me say temperature measurement or balances, the measurement of the mass, or the whole area of, let me say, concentration measurement of gases, concentration measurement of liquids, pH value measurement. That are all very slow measurements. And there is a settling time a very important parameter, because it gives you the time where you say, when I read the value after this time, then I have this rest of error from the dynamic behavior. Have you questions to this? No?
I think so.
Then I go a little bit back. What I have explained now is this so-called step function or jump function, where you go from one value to another value. You can unify it to one, so that you have every time the same function. In a time t0, you go from one value to another value, and what you looking for is the step response. And when you have a thermometer, the step response would going up and would go on this value. When you, let me say, give 80 centigrades water temperature on the thermometer, then you expect that the thermometer is in the status on 80 centigrades. But it must not be the case. You can also have 81 centigrades or 97 centigrades. Then you know there is an error in. But also this is a static behavior. The next point is what you can do in the time range. You see, we have here the time range. What we can do in the time range can we normally also do in the frequency range, because the frequency is 1 divided by the time. And when the frequency is 1 divided by the time, it is so that you can everything what you do in the time range, can you also do in the frequency range. And that is the case. We have here, for example, in the frequency range, the sinus function. The sinus function, you give on your system a sinus function, and what you get on the output side is also a sinus function, but with a different amplitude and with a phase shift. You have a phase shift on the output side because your device has a delay. And when you have a very slow device, the amplitude is going down from the input to the output side, is going down repeatedly, and you have also a phase shift. normally we work with the amplitude function. Both the amplitude function and the phase shift have the same information, but the amplitude is more easy to understand, that when you have a very slow device, that the amplitude on the output side is going down when you increase the frequency. The question is now, when would you test in the time range, and when would you test in the frequency range? And that is easy to answer with a practical example. Roughly, you can say, when you have very slow devices, it is more easy to test with the time function. You test in the time range. When you have very fast devices, it is better you test with the sinus function. For example, if you have an amplifier as a very fast device, maybe he can work in the range of megahertz, then it is so that you would have problems with the time function. You have to realize this step extremely fast when the amplifier is working in a megahertz range. And you have to look how the output side is developing. And also this in this extremely short time, and that is difficult. And for these fast devices, it is much more easier to generate a sinus function and look for the decrease of the amplitude of the output side when you increase the frequency. That is practically much more easier. On the other hand, when you have a slow device, let me make again the example with the thermometer. A thermometer, it is very easy to realize this step function. You put this thermometer in a pot of water and you have your step function. What would be the alternative? When you would like to test the thermometer with the sinus wave, then you have to increase and decrease the temperature in this pot of water in the shape of a sinus wave. And that is practically nearly no to realize. Theoretically, yes, but practically it is. It would be a lot of equipment, and it's too expensive, and it's not really good to realize. There is it much more easier to make a jump to put your thermometer in a pot of water, and then have you the time to look what is going on the output side. So that are the most important functions. We have some different test functions, but I think we can skip them. That is not so important for our lecture now. Yes, that is a step function. Here I have the amplitude and the phase response, and you see when you standardize the input and the output side, y divided by x, then the values are free of the units, so that it is completely, you can, let me say, you can compare an thermometer regarding the behavior with a balance, for example, because you are completely free of the units. And for what it is good is another question, but you are you describe only the time behavior. And here you see the frequency, omega divided by omega 0. And for omega 0, we take a frequency where we have no decrease of the output amplitude. Normally in electrical engineering is at 50 hertz. 50 hertz, that is like a standard where we say all devices have to work at 50 hertz, because that is also the frequency in the net, in especially in Europe. Not, I think not in Malaysia. I think you have a little bit different, 60 hertz, I think.
Yeah, you have 60.
Yes, you have 60. But between 50 and 60 hertz, the amplitude is that makes not a big difference.